more algebraically, more analytically to think about or evaluate limits. Please note that none of this is rigorous. We're not using what's called the epsilon delta definition. And so it's still nonetheless a good way to do these sorts of elementary limit problems. So let's first take a look at a process that's called substitution. And Britton brought this up in class today. And so sometimes, say, comma, for example, comma, if I gave you this particular limit problem, sometimes we're able to evaluate limits just by substituting the value in for x. So if we're evaluating the limit as x is approaching 2, if I substitute a 2 in and then evaluated that, what I would get is what? Sure, 7, but what does that represent? Good, yeah, that represents f of 2, right? If my original f is x squared plus 3. Right, so what we're doing with this technique is we're assuming for well-behaved functions, and we'll later call that functions that are continuous at a point, that the function at 2, which is 7, is also equal to the behavior of the function around 2. Okay, and that will always happen for nicely behaved functions. Certainly for the polynomial, the second degree quadratic x squared plus 3. Right, and so we can kind of justify that in the graph if we would like to. So let's look at x squared plus 3. And usually it takes 8 times for this to turn on. Oh, I'm getting there. Close. More than 8. Here we go. Hey, okay. So I'm going to go y equals, and I'm going to call that x squared plus 3. And I'm going to delete everything else and graph her up. And we could, from here, we can look at, oh, that's not a good window. Let's zoom standard. See if that helps. That's a little better. And so what we can see is that this parabola, which is shifted up 3 from the origin, and we can kind of look at we can trace as x is approaching 2, and we can note the y value from the left and from the right. Oh, there's the left, it's around 7, 6 and change, and then from the right. But let's look at the table just to verify that. I'm going to set it up. Since we're valuing limits x is going to 2, I'll start at 2. I got a nice change of table, 0.01, so I can really hone in on a nice tight neighborhood about 2. And I'm going to look at that table, and this table I think nicely illustrates that from both sides of 2, the limit as x is approaching 2 is indeed 7. And of course, this number here is what we're using when we use a substitution method, f of 2. By substituting, we get 7. And 7 is the value at 2, but it's also the behavior of the function, the same as the behavior of the function around 2, the limit. Okay? How about this problem? What if I asked you the limit as x is going to 0 of x times cosine of x? What do you think? Yeah, great idea. Let's split it up. So maybe that's the same as the product of their individual limits times the limit as x is going to 0 of cosine. Now I'm going to put a little asterisk here because that won't always work. Bonus points tomorrow if you can think of a case where you cannot split up the product into the product of 2 individual limits. Think about that. But anyway, I'm going to plug 0 in. I'm going to use substitution for both. Plug a 0 in here. Whoops. To get 0, of course. And then evaluate the cosine of 0, which, anyone remember what that is? No. It's 1. Yay! So it's really 0. The first 0 times the cosine of 0, which is 1. And that gives me the limit of 0. And again, we can kind of look at that graph. So let's look at x cosine x. Let's see if it works out. So I'm going to go back to y equals x cosine x. Nope. And I'm going to make sure I'm in the right mode. I am. I'm going to zoom trig it just to be funky. It goes from negative 2 pi to 2 pi. And here's my function, x cosine x. And I can trace it, and clearly you can kind of see that as x is tending towards 0 from the right, the y value is heading to 0. And as x is heading towards 0 from the left, y is going towards 0 as well. In fact, at 0 here, when we use substitution to plug in order to evaluate the limit, we also have a well-behaved function at 0. Okay, so that just justifies our substitution process. So to formalize substitution, what we're really doing is we're evaluating the limit as x is approaching c, or a, doesn't matter, by letting it equal the function value at c. And that's not always going to work. Okay? And that's not always going to work. I will tell you it always will work with any polynomial function, with a sine function, with y equals cosine of x. But that technique is not always going to work. So let's look at a case where it don't work. Right? So let's look at this example. So what if we can't substitute to evaluate a limit? Well, what can we do? Well, we can go back to a graph or table. That's cool. Right? But there are more analytic algebraic methods, and here's one of them. Right? So let's think, for example, about this particular. Well, let's stop going to 0. Let's make it crazy. Let's go to 1. Nope. Oh, sorry. And here's what I want. Yeah, that's what I want. And so what kind of function is this? If it were, yeah, good. It's called a rational function. We have a first-degree polynomial, a linear, on top of a quadratic, a second-degree polynomial. Right, now, a couple things to note. This function has a couple messy spots. Right? And those messy spots for this function happen essentially because we have a variable in the denominator. So it's important to note that this function, plus or minus 1, is just not in the domain. You cannot put negative nor positive 1 into this function. Okay? But wait a minute, I'm trying to evaluate the limit as x is going to 1. Well, if I plugged 1 in, I get 0 over 0, which is called the indeterminate form. Right? If I use substitution, plug a 1, oh, and that 0 over 0 is called indeterminate. Bonus points if you can tell me that means tomorrow. A lot of bonus points here. So that's right now meaningless. Okay? Just because you can't substitute doesn't necessarily mean that the limit does not exist as x is approaching that point. It just means at f of 1, it don't exist. Right? So how can I use substitution to evaluate the limit as x is approaching 1? Well, you can't, because f of 1 doesn't exist. But that doesn't mean the limit does not exist as x is heading towards 1. So here's what I'm going to do. I'm going to get my algebra hat on, and I'm going to remember that the difference of squares looks like this. Oh, and then I can simplify. That's right. And so this is the same as the limit as x is going to 1 of 1 over x plus 1. Now, what we've done is I've just changed this original function at 1 point. Because the original function, x could not be plus or minus 1. And now this modified function, it's the exact same as the other one, but it differs at only 1 point from the original function. Because now x can equal negative 1. So positive 1. It still cannot equal negative 1, right? It still can't plug negative 1 in for that x. So now what I've done is I've eliminated the issue with substitution, and now by factoring, and now I can substitute. So nothing wrong with plugging in a 1 in for this x. Right? I'm evaluating the limit as x is approaching 1. So I'm going to substitute now that I can. So I'm just going to plug in equals 1 over 1 plus 1, which is 1/2. Okay? So that's a way I would call it. We kind of get our algebra hat on if we can't initially substitute, and then substitute when we can. Right? So we plug that 1 in after we've eliminated the x minus 1 factor in the denominator. Okay, we've eliminated that point of discontinuity, essentially. So let's take a look, see if the graph agrees. Hopefully it will. We're going to look at y equals. I'm going to clear that up. Right, I need that in parentheses. It's the whole numerator, x minus 1, divided by the whole denominator, x squared minus 1. Right, I'm going to graph it. I'm going to zoom standard it, just get a little crazy. And here's my, I'm on connected mode, but that's okay. I'm going to make it a little clear. I'm going to x is going to 1, so I'm going to adjust this window a little bit. Let's go from -2 to 3. How about that? Let's get crazy. Right, there's my hyperbola, and you know what? This original function, if I trace it at 1, what's going to happen on this function? That's right, it's not defined. We should get an error, right? You cannot plug 1 in to this function, right? That will give you 0 in the denominator. Actually give you 0 over 0 indeterminate. But regardless, we can see that this function which really looks like this, but there's a little, oh, son of a gun. There's a hole right at 1, right? This function is undefined at 1. And this is a vertical asymptote. For some reason it's connecting it, because I think it's in connected mode. No, it's not. I'm not sure why it's connecting that. But regardless, here's x around x is 1. Right? And it looks like from the left of 1, we're heading towards 1/2. And from the right of 1, we're heading towards 1/2. Okay, so the graph justifies our analytic work over here. Okay, that's good for today. What I want you to think about for now is the following problem. Limit as x is going to -1 of that same x minus 1 over x squared minus 1. Okay, so this is the one problem I want you to think about for tomorrow. Good luck, have fun, and I will see you tomorrow.